Hello everyone. So this is the second hour of our unit Heat and Thermodynamics, and now we are going to talk about heat transfer. Even in heat transfer, in this hour we will focus on the conduction mode of heat transfer. We will talk about radiation and Newton's law of cooling in the next hour. So without wasting time, let's start learning heat transfer, the conduction mode. There are three modes of heat transfer. The three modes are named conduction, convection and radiation. But what is the meaning of these three modes and why are they different? Let's understand it. So first of all, let's think of conduction. Let's say we have a heat source. Here we have placed a candle. And if we place a metallic rod near this heat source, what does the heat source do? So the heat source provides energy. Now, due to the energy provided by the heat source to the molecule of the rod nearest to it, their energy will increase. As their energy will increase, their amplitude of vibration will increase. As their amplitude of vibration increases, they collide with the atoms in the next layer. When they collide, they transfer some part of energy to the atoms in the next layer. When some energy gets transferred, now these molecules starts vibrating with a higher amplitude, and then they start colliding vigorously with the molecules of the next layer and transferring energy to them. Then their energy increases and then they vibrate with more amplitude, and then they collide with the layer of molecules next to it, and then to the layer of molecules next to it, and then next to it, and then next to it. This mode of heat transfer is called the conduction mode of heat transfer. Notice that in this mode of heat transfer, the molecules are vibrating around their own mean position. They are just colliding and providing the energy to the next layer of molecules. No molecule is moving from the first position to the last position. So conduction is most dominant in solid and very less dominant in case of fluids. So let's talk about the next mode of heat transfer, which is convection. Now, not all substances are solids. There are fluids. Let's say we have a container filled with a fluid placed over a heat source. What will the heat source do? Sir, it will provide energy. Now, fluid molecules are not fixed to a position just like the molecules of solid. So once these molecules of fluid near the base of the container get energy, what do? So they start moving away. And as they move away with more energy, they collide with other molecules of fluid in the container as well as with the wall. In this process, they transfer the energy, and the transfer of this energy because of the temperature difference is the heat flow. So we say there is one more mode of heat transfer, which is called the convective mode of heat transfer. Now convection takes place predominantly in fluid. Since you have a fluid, the molecules are not at all at rest. When you provide the heat, the molecules gain energy, they move to other places, and during collision transfer the energy. Such a mode of heat transfer is called convective mode of heat transfer. There is nothing much to study in this particular part of heat transfer. Now let's move on to the last mode of heat transfer, which is the radiative mode of heat transfer. I don't know you know or not, every object above 0 Kelvin radiates. And every single object in this universe has temperature more than 0 Kelvin. So even you are radiating, even you are shining. It's just that people do not have the ability to see those radiations. So every object above 0 Kelvin radiates. And what do they radiate? They radiate EM waves. So sir, am I radiating EM waves? Yes, you are. Then why can't other people see me when the lights are turned off? Because the majority of EM waves you and me are radiating, they lie in infrared region and in microwave region. Since normal human beings can't see infrared radiation or microwaves without using a device, that's why we can't see each other in the absence of external light. This will become clear in the next hour when I focus especially on radiation. But this hour is dedicated to conduction. So let's first focus on conduction. So every object above 0 Kelvin radiates EM wave, and there is a heat transfer because of this radiation. So let's focus on conduction. So let's say we have a rod. If the left end of the rod is maintained at temperature T1 and the right end at temperature T2, if this has been told to us that T1 is greater than T2, this means that the temperature on the left end is more than the temperature on the right end. Because of this temperature difference, the heat will flow from higher temperature towards the lower temperature. Let's say this rate of heat flow is given as Q. So what is the meaning of rate of heat flow? Beta, rate of heat flow is the rate of transfer of heat with respect to time. So dQ by dt. So Q is the heat, the amount of energy that has been transferred upon infinitely small frame of time in which it has been transferred. So continuing with conduction, let's learn Fourier's law of heat transfer. Let's say we have this random shaped object. The two extremes of this random shaped object are maintained at temperature T1 and T2, and T1 is greater than T2. If we know that T1 is greater than T2, then the heat will flow from higher temperature to the lower temperature. We are talking about only conduction mode of heat transfer. As beta, in each and every part the heat flows from higher temperature to lower temperature, I can say moving from left to right, the temperature of this body will decrease. Let's go at a random distance and think of two layers which are at infinitely small separation from each other. Now, let's say here the temperature are T plus dt and T. In an infinitely small separation Tx, the temperature will even drop by an infinitely small amount dt. And let's say the area of cross section of the place where this heat flows is A, and the heat flow amount is Q. So Fourier's law of heat transfer tells us that the rate of heat flow Q, which is dQ by dt, which is the rate of heat flow, is directly proportional to the temperature gradient. Sir, what is temperature gradient? The rate of change of temperature with respect to length. That is the meaning of temperature gradient. So the infinitely small change in temperature upon the infinitely small length in which this temperature change takes place. So Q, which is equals to dQ by dt, is directly proportional to the temperature gradient. The greater the temperature gradient means the faster the temperature drops. More temperature gradient means more temperature change per unit length. So faster the temperature drops, the more will be the rate of heat transfer. You can think of it this way. It's not rocket science. Think that you have got two cubes made up of same material, same length. In first case, on the left hand side you have got temperature of 100 degrees centigrade, right hand side you have got temperature of 0 degrees centigrade. In the second case, you have got on left hand side temperature of 20 and on right hand side temperature of 0. I ask you in which case the rate of heat flow through this material will be more. So you'll say, sir, where the temperature drop per unit length will be more, there the rate of heat flow will be more. And you have told us the rate of heat flow is directly proportional to the temperature gradient. In the first case, in the same length, the temperature drop is 100. So the rate of change of temperature is more in the first case compared to second case. The temperature gradient in the first case is 5 times the temperature gradient in second case, because in the same length, in first case temperature drop is 100, in the second case the temperature drop is 20. So the temperature gradient in first case is 5 times. That's why if in the case 2 the rate of heat flow is Q, then in the first case the rate of heat flow will be 5Q, because the temperature gradient is 5 times. Second thing, the rate of heat flow is directly proportional to the cross-sectional area available for that heat flow. So think that for the same tube, same temperature drop, in the case 1, let's say you have a cross-sectional area A, and in the case 2, same thickness, same temperature drop, but next time you have a cross-sectional area 3A. So same length, same material, same temperature drop. Okay. If the cross-sectional area available for heat flow becomes 3 times, then the rate of heat flow will also become 3 times. So if in the first case the rate of heat flow is Q, in the second case the rate of heat flow will be 3Q. And every time physicists find this correlation of proportionality, they add up a proportionality constant. So here the proportionality constant added is called K, where K is said to be the conductivity of the material. Now, a good conductor transfers heat faster. See here, the better the conductor, the higher the value of K. And for everything else same, the temperature gradient and cross-sectional area same. The higher the conductivity, the more will be the rate of heat transfer, right? A better conductor conducts faster. So K is called conductivity. Sir, why is there a minus sign? The minus sign here, the negative sign here shows that the heat flow in direction of decreasing temperature. If I ask you, look at one small part. Here the temperature is T plus dt, here the temperature is T. Heat will flow from where to where? Sir, from higher to lower, so T plus dt to T. Now tell me, going from left to right, the change in temperature is positive or negative? Sir, going from left to right, the temperature decreases, so the change in temperature is negative. So remember that since the heat flow in direction of decreasing temperature, the heat flow in the direction where the temperature gradient is negative, where the temperature decreases. So as to balance the equation, we should multiply a minus sign. Just remember that this minus sign tells us that heat flows in direction of decreasing temperature. So moving on, let's learn about steady state. So what is the meaning of steady state? Where have you heard the word steady in your life? Ready, steady, go. Steady means something that do not change with time, something that is constant with time. So when do we say that a system is under steady state? As far as we are talking about heat transfer, we say that a system is under steady state when the temperature of each point on the system do not change with time. What do I mean by this? Let's think we have a rod, and let's say the left end of the rod is maintained at 100 degrees centigrade while the right end is maintained at 0 degrees centigrade. So as you move from left end to the right end, the temperature of each point will be different and the temperature will keep on decreasing. Now let's say somewhere the temperature of the rod is 80 degrees centigrade. So if you have a rod in which conduction heat current is flowing, the conduction heat current flows from higher temperature to lower temperature. Can I say that the temperature of each point on the rod is same? No. Sir, if the temperature of each point on the rod will be same, heat won't flow. For the heat to flow, the temperature of different point has to be different, and then the heat flows from higher temperature to the lower temperature. Good. Question is, what is the meaning of steady state? Sir, steady state means that it won't change with time. It means that if the temperature of a particular cross-sectional area is right now 80 degrees centigrade, even after some time it will be equal to 80 degrees centigrade. So the temperature of this particular cross-sectional area won't change with time. This is the meaning of steady state. And here, if there is some cross-sectional area at an even lower temperature than 80, let's say 30 degrees centigrade, its temperature won't change with time. A steady state does not mean that all the point on the rod will be at same temperature. No, it means that any small region on this rod will have the same temperature and it won't change with time. This is the meaning of steady state. So when the temperature of any given region, a small place, on the conductor do not change with time, we say that the conductor is under a steady state. So let's say we have got this rod under steady state. The temperature of left hand side is T1, the temperature of right hand side is T2, and let's say T1 is greater than T2. We know that the heat will flow from higher temperature to the lower temperature. So there will be a heat flow. Understand that again, this what I'm writing small q everywhere, this is the rate of heat flow, dq by dt. Now, under steady state, the temperature of any given place on this rod will be constant. It won't change with time. I'm not saying that T1 is same as T2 is same as T. Arre beta, if temperature will be same, why will the heat flow? I'm saying that the temperature of any given region on this rod do not change with time. The temperature of any point does not change with time. This is the meaning of steady state. Now let's say we have a case where we have got two cross-sectional areas P and Q. I ask you that if T1 is greater than T2, tell me where the temperature will be higher. The temperature will be higher at P or the temperature will be higher at Q. Sir, since the heat flow is from higher temperature to lower, and if I forget the rest of the part and I focus only on this part, In this part, the heat flow is from left to right. If I know that if in this part the heat flow is from left to right, then the temperature of P must be greater than temperature of Q. So going from left hand to the right hand, the temperature must be continuously decreasing. Now I tell you that this rod is under steady state. Tell me where the rate of heat flow will be more. The rate of heat flow will be more at P, or the rate of heat flow will be more at Q. So if you just focus on this much part between P and Q, the heat flow in will be more, or the heat flow out will be more. So we will say QP has to be equals to QQ. The rate of heat flow at the cross-sectional area P has to be equal to the rate of heat flow at the cross-sectional area Q. Why, sir? Why? Because beta of a simple argument. If let's say somebody says QP is more than QQ, the rate of heat flow in is more than the rate of heat flow out. If beta rate of heat flow in will be more than the rate of heat flow out, this particular part will store energy. If it will store energy, its temperature will increase. What I have said, we are talking about steady state. The temperature of each point remains constant. It does not change with time. So for the temperature to remain constant, the energy content has to be constant, and for energy content to be constant, the rate of heat flow in should be equal to rate of heat flow out. Similarly, if somebody argues that, sir, the rate of heat flow out should be greater than the rate of heat flow in. So if you look at this much part only, if the rate of heat flow out is more than the rate of heat flow in, then this particular part will be losing energy. And if it loses energy, its temperature will keep on decreasing. So QP has to be equals to QQ. That is, the rate of heat flow in through this much of cross-sectional area has to be equals to rate of heat flow out, so that the temperature of the part between P and Q remains constant. If the rate of heat flow in will be higher, then the temperature will rise. If the rate of heat flow out will be higher, then the temperature will decrease. For temperature of this part to be constant, the rate of heat flow in has to be same as the rate of heat flow out. Moving on, let's think of a question. Now rather than having a uniform rod, they have given me a truncated cone. So as you go from the left end to the right end of this conductor, you can see that the cross-sectional area is increasing. Question is, if the system is in steady state, made of uniform material, so let's say this whole cone, truncated cone, the front part is removed, this whole cone is made up of a uniform material, let's say copper, and T1 is greater than T2. You have to compare two things. First, where the rate of heat flow will be more, at the place where the cross-sectional area is less, or at the place where the cross-sectional area is more. Second thing, where the temperature gradient will be higher, at the place where the cross-sectional area is less, the rate of change of temperature with respect to length will be more, or at the place where the cross-sectional area is more, the rate of change of temperature with respect to length will be more. So these are the two questions you have to answer. They have told me that this truncated cone is under steady state. It means that the temperature of any part do not change with time. If I just focus on the part of this truncated cone between X and Y, the temperature of every point here remains constant. It means that the rate of heat inflow has to be equal to rate of heat outflow. Otherwise, the temperature won't remain constant. So, as the system is in steady state, the rate of heat flow at X should be equal to the rate of heat flow at Y. Otherwise, beta, the temperature can't be constant. The temperature of this part in between may start to increase or decrease. The next question, where the temperature gradient is more. We have learned the Fourier's law of heat transfer. It says that Q equals to Ka del T by del X, the rate of change of temperature with respect to length, which is also called temperature gradient. For both the cross section X and Y, the rate of heat flow is same. Since it is made up of uniform material, K is same. So if Q and K are same, you can say that A into del T by del X means the cross-sectional area times the temperature gradient has to be equals to constant. And if the cross-sectional area times the temperature gradient has to be constant, wherever the cross-sectional area will be more, the temperature gradient will be less. Since we can see in the diagram at the position Y, The cross sectional area is more, so there the temperature gradient has to be less. So as heat flow rate Q and K is same at both the places, where the area is more, the temperature gradient will be less. So since the area is more at Y, the temperature gradient will be less at Y. Hence we can say that the temperature gradient at X will be more than the temperature gradient at Y. So this is why knowing steady state is important. So let's discuss the case of uniform rod. If we have a uniform rod under steady state, let's say we have this rod. On the left hand temperature is T1 and on the right hand temperature is T2. Given that T1 is greater than T2 and this rod has a length L. We know that if we have a uniform rod under steady state, heat will flow from higher temperature to lower temperature. Under steady state, throughout the cross section, the rate of heat flow Q will be same. So we know that Q equals to Ka del T by del X from the Fourier law. So why you haven't placed the minus sign? We are just looking at the magnitude right now. We know that Q, K and A is going to be same for the entire rod. So as Q, K and A is same everywhere, del T by del X is also constant. Since you know that the temperature gradient is constant, the rate of change of temperature with respect to length is constant, you can simply write the temperature gradient to be equal to the change in temperature T1 minus T2 upon the length in which this temperature change takes place, which is L. So you will get the temperature gradient to be T1 minus T2 by L. Now, if you need to find the temperature at a random distance x from the left end, and let's say at this place the temperature is Tx. How to find Tx? It is quite easy. You will say the temperature drop from the left end till the distance x will be given by T1 minus Tx. And this T1 minus Tx has to be equal to the temperature gradient multiplied by length. But what is the meaning of temperature gradient? The rate of change of temperature with respect to length. So if I tell you that temperature gradient is T1 minus T2 by L and the length is x, so in a length x, how much temperature drop will take place? So you will say temperature gradient multiplied by length. So you will say the temperature difference in a length x has to be equals to temperature gradient T1 minus T2 by L into x. To find the temperature at distance x, bring this to the right hand side and this whole quantity T1 minus T2 into x by L to the left hand side. So you will say the temperature at distance x will be nothing but T1 minus T2 into x by L. T1 minus T2 into x by L. So this will be the temperature at a distance x from the left hand. This is how you find it. So moving on. Comparison of heat transfer with Ohm's law, or you can say with current electricity. If we have a rod, a conductor rod, which conductor? Electrical conductor. And let's say we have placed this electrical conductor between a potential drop. So on the left hand side, potential is V1, on the right hand side, potential is V2, and V1 is greater than V2. So just the way heat flows from high temperature to low temperature, the current flows from higher potential towards lower potential. So let's say here the current flow is I. How do we find this current flow? Sir, Ohm's law. Ohm's law tells us that the potential drop has to be equals to I into R. Since the potential drop has to be equals to I into R, and we can write the resistance as rho L by A. What is rho? Resistivity. What is L? Length of the conductor. What is A? The cross-sectional area through which the current flows. So in place of R, substituting rho L by A, you will say the potential drop V1 minus V2 equals to I into rho L by A. You can rewrite this thing as the current flow I equals to, bring the A up and rho L down. So you get A delta V by rho L. This will be the current flow. If I ask you what is current, you will say, sir, current is the rate of flow of charge with respect to time. That is what current is. Now, I want you to remember that the resistance of this particular conductor is given by rho L by A. And how do we compare this with Fourier's law of heat transfer? So now think of the rod. On the left hand side temperature is T1, right hand side temperature is T2. It is a uniform rod, so the temperature gradient will be simply T1 minus T2 by L. You will say the rate of heat flow, small q, equals to Ka times temperature difference T1 minus T2 by L. You can rearrange it and write the rate of heat flow equals to K into A into delta T by L. Now I want you to focus on these two parts. The rate of heat flow, the rate of charge flow equals to conductivity in numerator, resistivity in denominator. Cross-sectional area, cross-sectional area. Cross-sectional area through which the heat flows, cross-sectional area through which the charge flows. Temperature difference, potential difference. Length of the conductor, length of the conductor. So there is a similarity between Ohm's law and Fourier's law of heat transfer. Now, just the way for current electricity we use the term resistance very often, now we are going to use a term called thermal resistance. So we say that the thermal resistance equals to L by Ka. You know that electrical resistance is rho L by A. Beta, what is rho? Electrical resistivity. What is L? Length. What is A? Cross-sectional area. You know that resistivity and conductivity are reciprocal. So if you are getting electrical resistivity in the numerator, you will get thermal conductivity in the denominator. So just because you already remember R equals to rho L by A, it's very easy to remember. Even for thermal, we write rho thermal L by A, but since they never talk in terms of resistivity thermal, think of it as thermal conductivity in the reciprocal, in the denominator. So you need to remember that the thermal resistance is given by L by Ka. One more thing I will like to emphasize here. What is I? The rate of flow of charge with respect to time. It's called current. What is Q? The rate of flow of heat with respect to time. Q equals to dQ by dt. It is beta also called thermal current. It is also called thermal current. And in the next hour, I will tell this is also called thermal power, but that is for some other time. That is for next hour. So Q is thermal current and the thermal resistance is L by Ka. So let's do some questions using the concept of Ohm's law in Fourier's law of heat transfer. So the first question, there is a composite rod. Here we have got a length L1, conductivity K1, length L2, conductivity K2, and the cross-sectional area through which the heat flow is A. Question is, find the rate of heat flow and temperature of the junction. So you need to find two things. First, what will be the rate of heat flow and what will be the temperature of this junction. So let's see. Compare this with current electricity. Rather than thinking of two thermal conductors, think of two thermal resistors. So you will say the temperature of the left hand is T1, the temperature of the right hand is T2. Our mission is to find T dash, that is the temperature of the junction. Now think of two thermal resistances, R thermal 1 and R thermal 2. Just the way in current electricity you say that current equals to potential drop upon resistance. Here you will say thermal current equals to temperature drop upon thermal resistance. Now tell me, these two resistances are in series or parallel? They are in series. Same thermal current flows through them. So you will use R equivalent equals to R1 plus R2. So your simply rate of heat flow will be nothing but the temperature difference upon the total thermal resistance of the system, which is R thermal 1 plus R thermal 2. Now all you have to do is substitute data. In place of R thermal 1, remember that R thermal is beta L by Ka. In place of R thermal 1, substitute L1 by K1A. In place of R thermal 2, substitute L2 by K2A. So you get T1 minus T2 upon L1 by K1A plus L2 by K2. Now multiply K1, K2A, K1, K2A to each term. What you get is T1 minus T2 into K1, K2A. When you multiply in denominator K1, K2A, in the first term, K1A get cancelled, so here you get a K2. When you multiply K1, K2A to L2 by K2A, the K2A get cancelled and you get L2 K1. So this is the rate of heat flow. They have asked me one more thing. What is the temperature of the junction? To determine the temperature of the junction, we know that the heat flow rate through both of them will be same. Why? Because they are in steady state. So we can say the rate of heat flow in the first resistor, which is nothing but the temperature difference across it, T1 minus T dash upon R thermal 1. This has to be equal to the rate of heat flow through the second thermal resistor, which will be T dash minus T2 upon R thermal 2. Once you have done this, game over. Bring this R thermal 2 up, R thermal 1 up. Cross multiply, you will get T1 R thermal 2 minus T dash R thermal 2 equals to T dash R thermal 1 minus T2 R thermal 1. Bring the term of T dash to one side. So bring this term of T dash to right and this term of T2 R thermal 1 to left. So you will get T dash times R thermal 1 plus R thermal 2 equals to T1 R thermal 2 plus T2 R thermal 1. So you can say the temperature of junction has to be equals to T1 R thermal 2 plus T2 R thermal 1 upon R thermal 1 plus R thermal 2. Not at all a difficult thing. But it looks big. It's an easy operation. Now beta, in place of R thermal 2, substitute L2 by K2A. In place of R thermal 1, substitute L1 by K1A. When you substitute, it looks even ugly. Then multiply each term with K1, K2A and you get the final result. This looks ugly, but it's very easy job. Just remember that R thermal is L by Ka and keep applying the same concepts of current electricity here. Moving on. The next question is, there are two rods of length L1 and L2. They have the same cross-sectional area. They have different thermal conductivity K1 and K2 and they form a composite system. Question is, determine the K equivalent of the system. So removing these two rods, if I place a single rod, what has to be its equivalent thermal conductivity so that it acts like the composite system of these two rods. So if we replace these two rods and then place only a single rod, that single rod will have length equals to L1 plus L2, the length of this composite system. That single rod will have a cross-sectional area A and it will have, let's say, a thermal conductivity K equivalent. We know that if this single rod has to be equivalent of these two rods connected in series, then the R thermal equivalent of this single rod has to be equals to R thermal 1 plus R thermal 2. So you will simply say R thermal equivalent has to be equals to R thermal 1 plus R thermal 2. What is R thermal? Sir, L by Ka. For this single rod, the length is L1 plus L2. The thermal conductivity is K equivalent and the cross-sectional area is a substitute. For the first rod, R thermal 1 is L1 by K1A. For the second rod, R thermal is L2 by K2A. So if you cancel out bachcho A and you play little bit, you will get K equivalent. Bring this up equals to L1 plus L2 by L1 by K1 plus L2 by K2. So multiplying K1 K2 to each term in numerator and denominator. So here bachcho, you will get L1 K2 plus L2 K1. So you can write K equivalent equals to L1 plus L2 upon L1 by K1 plus L2 by K2. Multiply K1 K2 to each term. You will get the answer. Okay. Next question. Now we have got two rods in parallel. Both the rods have same length L, but they have different cross-sectional area. The upper one has got cross-sectional area A1, while the lower one has cross-sectional area A2. They have different thermal conductivity K1 and K2, and the question is, find the equivalent conductivity of system. So replacing these two rods, if you place only a single rod, what has to be the equivalent thermal conductivity of that rod? Now, in the combined system of these two rods, the combined area available for heat flow is A1 plus A2. So rather than thinking of these two rods, think of a single rod in which the area available for flow of heat is A1 plus A2, whose length is L and whose thermal conductivity is K equivalent. So for resistances in parallel, we know that 1 upon R equivalent equals to 1 by R1 plus 1 by R2. Now we know that R thermal equals to L by Ka. Here we have to substitute 1 by R thermal in each term. So 1 by R thermal will be equals to Ka by L. First, what is the value of Ka by L for the composite system? So K is K equivalent. Area is A1 plus A2 by L. So K equivalent into A1 plus A2 by L. What is 1 by R thermal? So 1 upon R thermal 1 will be K1 A1 by L. And 1 upon R thermal 2 will be K2 A2 by L. Substitute that. So you get K1 A1 by L plus K2 A2 by L. Now from each term, cancel out L. So what you get is K equivalent equals to K1 A1 plus K2 A2 by A1 plus A2. A simple question. Now let's see the next question which will be asked in current, electricity, capacitor, everywhere. So the question goes like this. There are three rods having length L1, L2, L3, having conductivity K1, K2, K3, having the same cross-sectional area A, or maybe different cross-sectional area A1, A2, A3. Now they are joined at a point. They will ask you what is the temperature of the junction. In this particular case of heat transfer, since I am dealing in terms of variable, I just want you to write the equation that how will you find the temperature of the junction. And this single question comes many a time in many different chapters. So write the equation to determine the temperature of the junction. What to do? So rather than thinking of three conductors through which heat flow, think of three thermal resistances. Now assume that the thermal current in the first one is Q1 down, the thermal current in second one is Q2, and the thermal current in third one is Q3. Once you have assumed these three thermal currents, you can say that Q1 plus Q2 plus Q3 has to be equals to 0. If I draw here three wires and ask you, beta, if the current in these three wires is I1, I2 and I3, what is the correlation between I1, I2 and I3? You will say, sir, from Kirchhoff's current law, the current coming to the junction has to be equal to current going away from the junction. So I will write that I1 plus I2 plus I3 will be equals to 0, because no current is going away from the junction. All the current is just going towards the junction. So as to find the temperature of the junction, assuming the temperature of junction to be T dash, we can write first the equation of KCL for thermal, and we will write Q1 plus Q2 plus Q3 has to be equals to 0. Now bachcho, how will you write Q1? You will write Q1 to be temperature difference across the thermal resistance divided by its thermal resistance. So Q1 will be written as T1 minus T dash by R thermal 1. Q2 will be written as T2 minus T dash by R thermal 2, and Q3 will be written as T3 minus T dash upon R thermal 3. So you get T1 minus T dash upon R thermal 1 plus T2 minus T dash upon R thermal 2 plus T3 minus T dash upon R thermal 3 equals to 0. Now beta, substituting R thermal 1, R thermal 2, R thermal 3 as L1 by K1, A1, L2 by K2, A2, L3 by K3, A3. You can solve for T dash. I'm just telling you how to make the equation. Once you know how to make the equation, you will be able to solve this question in paper easily. So focus on concept. I know that in paper, they will give you simple data like, length as L, 2L and L by 2. So you get good value of their thermal resistances. Okay. Moving on to the next case, the Wheatstone bridge for thermal conduction. You have learned that there is something called a Wheatstone bridge. If we have got four resistance R1, R2, R3, R4, and there is one more resistance joining in middle, let's call R5, then no current flows through R5. No current flows through R5 when R1 by R2 equals to R3 by R4, or beta R1 R4 equals to R2 R3, R1 R4 equals to R2 R3, then no current flows through R5. If no current flows through R5, you can say that there is no potential difference across R5. So if these 2 points have name A and B, then you can say for no current to flow through R5, potential at A has to be same as the potential at B, right? So now let's see balanced Wheatstone bridge for conduction current. So let's say here we have got four rods of length L1, conductivity K1, length L2, conductivity K2, length L3, conductivity K3, length L4, conductivity K4, and their cross-section areas are A1, A2, A3 and A4. If you want these 2 points X and Y to be at same temperature, so that if you place another rod between them, no heat flows through this rod, then what is the condition? So you will say, sir, the same condition as in the case of current electricity. So you will say R thermal 1 into R thermal 4 has to be equals to R thermal 3 into R thermal 2. So for temperature at X to be same as the temperature of Y, so that if a rod is placed between X and Y, no heat flows through it, you will say that R thermal 1 into R thermal 4 has to be same as R thermal 3 into R thermal 2. Now you can write R thermal 1 as L1 by K1A1, R thermal 4 as L4 by K4A4, R thermal 2 as L2 by K2A2, and R thermal 3 as L3 by K3A3. So this is how you write the equation. This is not at all a difficult thing, but you should know the condition of balanced Wheatstone bridge. So Wheatstone bridge is said to be balanced when no current flows through the middle line, and for that these two temperatures have to be same, and for these two temperatures to be same, the condition has to be satisfied, which is R thermal 1 into R thermal 4 equals to R thermal 2 into R thermal 3. Moving on, how does the ice grows on a lake? So if we have a lake and the surrounding temperature is sub-zero, think of the interface of the ice and water. Let's say here you have got water and this is ice. Then at the interface of ice and water, where the ice and water coexist, the temperature has to be 0 degrees centigrade. So at the ice water interface, the temperature is 0, and in the surrounding outside the lake, the temperature is sub-zero. So where do you have higher temperature? So sir, 0 is more than sub-zero. Hence, the heat will flow from the ice water interface into the surrounding. This heat will flow through the thickness of ice. Now, how much time it will take for growth of ice? That's what we need to derive here. So you will say the rate of heat flow through this ice will be equals to Ka theta by x. Sir, what is theta? The temperature difference. Beta 0 minus theta gives you theta, temperature difference. And sir, what is x? X is the thickness of ice at any given instant. So let's say at any given instant, when the thickness of this ice between the ice water layer and the surface is x, you will say that the rate of heat flow will be Ka into theta by x. Sir, what is K? Conductivity of ice. What is A? The area of cross sectional through which you are assuming the heat to flow and you are observing. Now dq by dt, you know now, q is what? Rate of heat flow. dq by dt. So dq by dt equals to Ka theta by x. Now because of the heat moving out from the ice water interface, what will happen? Because of the heat moving out of the ice water interface, what will happen? Sir, if heat goes out of the ice water interface, more ice will be formed. So let's say in an infinitely small frame of time dt, some heat will flow out. How much? dq. And this infinitely small amount of heat that flows out will be equal to the rate of heat flow multiplied by dt. Because of this infinitely small heat flow, there will be an infinitely small thickness of ice formation. Now the area we are considering is A, and let's say a dx thickness, infinitely small thickness of ice grows there. So if an infinitely small thickness dx of ice grows, the infinitely small volume of ice that will grow will be equal to the cross sectional area into the infinitely small thickness. So the infinitely small mass of ice that will grow is density of ice into the infinitely small volume of ice that has grown. So the infinitely small mass of ice that grows is density of ice into A dx. Now, how much heat must have gone out from the ice water interface to form dm mass of ice? So you will say the infinitely small amount of heat that must go out has to be equals to infinitely small mass times the latent heat of fusion. So that will be density of ice into A dx into the latent heat of fusion. So beta, you can say dq equals to the infinitely small mass of ice formed multiplied by the latent heat of fusion. So dq equals to infinitely small mass of ice formed, which will be nothing but the density of ice multiplied by infinitely small volume of ice formed, cross sectional area A and thickness dx. Once you know dq equals to this, substitute dq here. So you will write the density of ice into A into dx into Lf, which is the infinitely small amount of energy gone on, upon dt equals to Ka theta by x. Now bachcho, bring this x to the left hand side, this dt to the right hand side, and this A get cancelled and this density of ice down here. as well as latent heat of fusion down here. So what you get is x dx on the left hand side equals to a get cancelled. So you get k theta dt upon LF and density of ice. So this is what you get. Now integrating both the side, the thickness of ice from 0 to x and the time taken for this growth of ice from 0 to t, you get x square by 2 equals to k theta integrating of dt from 0 to t gives you t upon density of ice upon the latent heat of fusion. So this is the formula that you have to remember. Now what you have to exactly remember here is that x square proportional to t, or the time taken for growth is proportional to x square. Now beta, if time taken for growth is proportional to x square, to double the thickness, the time taken will be 4 times. To triple the thickness, the time taken will be 9 times. To make the thickness of the ice 10 times, the time taken will be 100 times. Okay. Now here I want to emphasize on one more thing. The time taken for the thickness to go from 0 to x is proportional to x square. If I ask you, beta, from 0 to 1 mm, if the time taken is t, then from 1 mm to 2 mm, what will be the time taken? So you will say the time taken proportional to x square. If from 0 to 1 mm, the time taken is t, then from 0 to 2 mm, for double the thickness, the time taken has to be 4 times 40. So beta, from 1 to 2 mm, from 0 to 2, 40. So from 1 mm to 2 mm, the time taken has to be 40 minus t will be 3t. So we can apply in a way Galileo's law of freely falling body here as well. For equal consecutive growth in the thickness of ice, starting from 0, for equal consecutive growth in the thickness of ice, the time taken is in the ratio 1:3:5:7:9. For the first 1 mm, if the time taken is t, then for the next 1 mm, from 1 mm to 2 mm, the time taken is 3t. So remember this statement. Starting from 0, no thickness, the ratio of time required for consecutive equal growth of thickness is in the ratio 1:3:5:7:9 and so on. So if for the growth of 0 to 5 mm, let's say the time taken is 10 minutes. Then for the further growth of ice from 5 mm to 10 mm, for the next 5 mm, the time taken will be 3 times, that will be 30 minutes. So this is what the statement means, and I recommend you to remember this last statement. Moving on to the next part. The question here says that here we have a rod. If the rod is under steady state and the graph shows temperature profile, what is the meaning of temperature profile? How does the temperature changes with the length? Moving from left to right, what happens to the conductivity of rod? So going from left hand to right hand, what happens to the conductivity of the rod? So you can say on the left hand, the temperature drops slowly, and towards the right hand, the temperature drops faster. Tell me, across which type of material you find the temperature drop to be more? A good conductor or a bad conductor? I ask this question from students all the time. Think that you have got flame. Okay, 2 burners with flame. On one burner, you have got a metal plate, and on the second burner, you have got an ebonite plate, a non-conducting plate. And I ask you, you have to place your hand over one of the plate. On which plate you will place your hand? You will say, sir, I will place my hand over the non-conducting plate, because the temperature at the top will be way cooler than the temperature at the bottom. In the case of metal plate, conducting plate, the temperature at the top and bottom will be nearly same. So I ask you the question again. Across which type of material you find more temperature difference? A good conductor or a bad conductor? Sir, across a bad conductor, the temperature difference is more. And across a good conductor, the temperature difference is less. If you look at the temperature profile of this particular rod, near the left hand, the temperature is nearly the same. Temperature drops very less. But as you move forward along its length, the temperature starts to drop drastically. So when the temperature fall is more, it is a good conductor or a bad conductor? Sir, across a bad conductor, the temperature fall is higher. That's why I can say moving from left end to right end, the conductivity keeps on decreasing. This thing starts becoming a bad conductor. Sir, I did not like this solution. Then there is another solution. We will use mathematics. So we know that Q equals to Ka del T by del X. Initially, the temperature does not drop quickly. It is nearly constant. It means that del T by del X is 0. Temperature is nearly constant. It means that del T by del X is 0. So the temperature gradient is less. Later the temperature decreases faster, right? In less length you get more temperature drop. So as on moving from left to right, under steady state, we know that Q has to be same. A is given same. So where the magnitude of temperature gradient will be more, there the conductivity has to be less. So as on moving from left to right, the magnitude of temperature gradient increases, we can say that conductivity decreases. But I know that you liked the first solution. So better rewind it and listen it again. Let's move on to the next example of same time. So this time example is, here we have got a composite rod. The left part have a length L1, conductivity K1, right part has a length L2, conductivity K2. The temperature of the two extremes are T1 and T2. Question is, looking at the temperature profile, determine which rod has higher conductivity. So this is what the temperature profile looks like. So from 0 to L1, the temperature drops. And then from L1 till L1 plus L2, temperature further drops. But just by looking at this graph, I have to tell which is a better conductor, which has got higher conductivity. How to compare K1 and K2? So you will say, sir, under steady state, the rate of heat flow in both the rods will be same. From Q equals to Ka del T by del X, I can say the rod for which the temperature gradient has more magnitude, it will have a lower conductivity. As Q is same, A is same. The rod which has got greater temperature gradient, it will have a lesser conductivity. Now temperature gradient, just by looking at slope, you can see across which rod the temperature falls faster. So sir, across the first rod the temperature falls faster, and across the second rod the temperature falls slowly. Temperature falls less across a good conductor, metal, and temperature falls more across a bad conductor. That's why I can say that K2 is better conductor than K1, so K2 has to be more than K1. Or you can say, where del T by del X is more, temperature gradient is more, there the conductivity has to be less. Since for the first rod, the slope is more, the temperature gradient is more, there the conductivity will be less, so K1 has to be less than K2. So as Q and A are same, where magnitude of temperature gradient is greater, K is less, hence beta K1 will be less than K2. The second rod is a better conductor compared to the first rod. Now, one single thing we need to understand about convection. Let's say we have a hot wall and we have a cold wall. So what is the meaning of hot wall, cold wall? A wall at higher temperature and a wall at lower temperature. And there is some fluid filled between these two walls. Now this fluid can be a liquid or a gas. The molecules of fluid are not at rest, so these molecules will collide with the hot wall. When they are in contact with the hot wall, they will take some energy from them, and then over the period of time they will go and collide with the cold wall. When they will collide with the wall at lower temperature, they will transfer some heat to this wall, and because of these multiple collisions, because of the millions of molecules moving in the fluid, there will be a net heat transfer from the hot wall to the cold wall. This type of heat transfer is called convection. Now there is only one thing you should know. What is gravity aided at convection? Tell me, if you have two cases in real world, case 1 in which hot plate or higher temperature plate is placed above the cold plate, or the case 2 where cold plate is placed above the hot plate and there is air filled between them. One of the convective heat transfer is gravity aided and one of them is gravity opposed. You just have to tell me which one is gravity aided and which one is gravity opposed. Sir, if you place cold plate at the bottom and hot plate at the top, when the air near the hot plate gets heat from the hot plate, it becomes lighter. So the density decreases. And because of lower density, then compared to the cold air, it won't be able to move down. To the contrary, if you plate hot plate below the cold plate, then the molecules of air near the hot plate will get energy from the hot plate. These molecules of air will expand and hence the density decreases. And the air near the cold plate would have got cooled and its density would have increased. So because of this difference in density, the lighter gas, the hotter gas will try to move up while the colder gas, the denser gas will try to move down. So you should know there is something called gravity aided convection and gravity opposed convection. When you place the hot plate above the cold plate, it is gravity opposed convection. Why? Because the air near the hot plate gets hot, its density decreases, while the air near the cold plate gets cold, its density increases. So its density is less, its density is more. So the less dense stays on the top of the more dense. There is no circulation current. But if you place hot plate under the cold plate, then the air near the hot plate gets hot, its density decreases, while air near the cold plate gets cold, its density increases. Now because the denser substance, the denser fluid is above the lighter fluid, the denser fluid moves down and the lighter fluid moves up. Once the lighter fluid, the hotter fluid moves up, it transfers the heat to the cold plate. Its temperature decreases, it becomes dense, and again this circulatory currents are formed. And this is common sense. When we cook food in our home, we keep the pressure cooker over the burner, not under it, because gravity aids convection, that is heat transfer in the upward direction. That's all in this hour. See you guys in next hour where we will talk about radiation. Bye bye.